Hello and welcome to another video. In this video we're going to be working on make sum divisible by p. And I think this problem is pretty tough for a medium. I guess it has a low acceptance rate. So in this one you have an array of positive integers and you want to return or remove the small subarray such that the sum of the remaining elements is divisible by p. It's not allowed to remove the whole array. Return the length of the small subarray such that you need to remove. Subarray is defined as a contiguous block of elements within the array. So in this example, we can get rid of this. And then this is divisible by 6. And in this example, we can get rid of this. And that's divisible by 6. And then here, we don't need to remove anything. So right away from this first example, is there already a hint already? So if we can get the sum, right? So like get the sum. If it's divisible, divisible by p, we are done, right? We just return 0 because like we don't need to remove anything. However, what if it's not divisible by p? Like, let's go look at this example. So in this example, the sum here is 16, yeah, and it's not divisible by p, right? So there's actually a mod 7 here. And so what does this mod 7 tells us? This mod 7 tells us that we have to remove a subarray that has this mod, because then the rest of it will be 0, right? So basically, there's a remainder 7 here. So this number could be really big, right? Like imagine this number some random number, like this. You know, obviously this is not the case, but let's say it's this. We don't have to necessarily remove 7. We just have to remove something that when we mod it by 9, we get 7. So we can remove 7, we can remove 16, we can remove like so on, right? 25, any of these, as long as we're not removing the whole subarray. Because like, let's say we remove 25, like, and this is actually the case, then basically we'll get this minus 25. And so 25 is like 9 goes into it twice perfectly, so it would be the same thing as removing 7. So if there's a remainder 7, it's the same thing as this. And we can demonstrate this with a smaller number. So let's say we have like 25, and we're dividing by 6 or something. And we get, and we get 1. So we can subtract 1, right? Like we can just do like 25 minus 1. That'll be 24, and that will go into 6 evenly. Or we can subtract more stuff. So we can basically keep adding 6. So we can subtract 1, we can subtract 7. So if we subtract 7, we'll get 18, which also mod 6 is remainder 0. Then we can also subtract 13, and so on and so on and so on. So you can subtract the remainder. So the equation would be like the mod plus x times p, where p is the number you're dividing by and x is any number. And if you subtract any one of these things, you will get a remainder 0. So to reword our original problem here, our remainder is 7. So we need to subtract something we need to subtract some subarray, right? Some subarray where the total mod 9 is 7. And if that's the case, then we're basically able to solve this. So 7 mod 9 is 7, but this can be some other thing, right? Like I said, if the subarray was like 6, 3, and then some other stuff, 5, 2, 9, we can also subtract something like this. That would also work, and so on. So hopefully that makes sense. So basically, we can get a total, and then we can figure out like what we need to actually subtract. And then basically our problem is given some remainder, what is the smallest subarray with that remainder that is not the entire array, right? And it's kind of hard to figure that out, right? So like in this problem, basically we're saying what's the smallest subarray that subarray total mod 9 is 7. And how would we figure that out? And that part's kind of tricky. But basically you can kind of I think there's like some other problems with modulo arithmetic, but if you have some mod, you can basically store like a prefix mod at every position. So for this 6352, let's just drawn right in here. So at this 6, 3, 5, 2. So we can store basically like a prefix mod, and we're actually going to include -1, kind of like a prefix sum. So this include like the empty array. So at -1, the prefix mod, so basically like 0 mod 9 is 0. And let's actually just copy this, so then we can, our prefix mod thing will be down here. So this will just be the numbers, and then this will be the prefix mod. Okay, so for -1, this is 0. For 6 mod 9 is 6. And then we basically can add these up. So imagine, like, we're not going to get a prefix sum, but we're going to maintain a cumulative sum. So it'd be like 6, 9, 14, and then 16, right? And so basically what you do, and also because we're only doing modulos, anytime your number is bigger than 9, we can just mod it by 9. So instead of storing 9 here, we can just store like 5 and 7. So basically just maintain a cumulative sum and just keep dividing by 9, because anything bigger than 9 doesn't matter, because all we care about is the remainder. So basically, yeah, here the remainder is 6, 0, 5, and 7. Yeah. And this is what we care about. And so if we have a subarray, like let's say we're over here, if we have a subarray that we know that like if we add up all of these elements and mod it by 9, our remainder will be 5, and it is, right? That would be basically equivalent to this guy. What do we need to delete to make the, like what subarray do we need to make to delete? Like, let's say this was the end of our subarray, which it's not, but let's say it was. What would we need to delete to make the total, basically, like 0, right? Like what are we deleting? And so the thing we would have to delete here is we'd have to delete, like, if this is mod 5, this is kind of the same as the problem like a few days ago where you're like adding up remainders. If this remainder is 5 and we need to delete something with a remainder 7, then we actually need to have a remainder of 7. Because in order to go from a remainder 7 to a remainder 5, if you think about it, by dividing by 9, like if something mod 9, if x mod 9 is remainder 7, and y mod 9 is remainder 5, and y is x plus some other number, that difference has to have remainder 7. Right? Because it's the same as adding up remainders. Because if this is remainder 7 and this is remainder 5, then we basically had a remainder 7, we added another remainder 7, and now we have a remainder 5, right? So any numbers will be like that. So for example, if we have like 25 has remainder 7, and then we add just like 7, and we mod this by 9, yeah, then this will be remainder 5. So hopefully that makes sense. I think this is the confusing part of this problem, is like, given a remainder, what's the other remainder I need to look for that I needed to have to delete something here? And if I'm able to do that, then I can get rid of a subarray. So hopefully that makes sense. So because here's a 5, we're looking for a 7. And the general formula would be something like, you take whatever remainder you have, and you can add p just to make sure your number is never negative, and then you can just mod it by the remainder. Actually, let's see. You take the remainder that you have, you add p, and which would be like, in this case, it would be 14. No, I don't think we can do that. I think it would be more like p minus that or something, right? Let's think. Okay, so it would actually be the remainder that you have currently minus the remainder you're trying to subtract. So in this case, it would be 7, right? Because we're trying to get rid of something with the remainder 7. Now, this is where we can add p, just because, like, let's say the remainder we have is 5, and we need to subtract 7, this will be negative. So we can just always add p here to make this positive, and then we can mod this by p. So that would basically be 5 minus 7 plus 9 mod 9. And so this will be 7 mod 9, which will be 7. So that's the number we're looking for. So hopefully that makes sense. Like, if you have one remainder, what's the other remainder you need to look for? And if you have a 5 and you had a 7, that subarray between those has to have remainder 7, and then we can get rid of that. So now that we know, like, given a number, what's the other number we have to look for? Like what's the best way to do this? Well, now we can just have a dictionary of like remainder and index. And then if we had some remainder and we have some other remainder and we know we're looking for that one, like in this case, let's say we're looking for a 7. Let's say the 7 occurred here. Then this subarray here is going to be the thing we need to remove. Because if this was a 7 and this is a 5, that means the thing in between them had a 7, so that's what we need to remove. And then we can just figure that out from like what index do we have, what index did we need, and so on. So now we can go through all these examples because they're kind of short using this, and hopefully it'll make more sense. And let me actually rebuild these numbers to make it easier to see as well. But yeah, that's kind of the tricky part of this problem. It's like, given a remainder, what remainder did I need to have to make sure that that subarray that I'm removing makes this thing work? So here. Okay, so like I said, at -1, so this is basically at index -1, the remainder is 0. Yeah, and all these should be fine. Okay, so here we have a remainder 6. And remember, the array we're trying to get rid of is remainder 7. So if we're trying to get rid of 7 and we had a 6, we basically needed to have the same thing, right? So it's going to be what we have minus what we are trying to get rid of plus p, which is 9 in this case, mod 9. So this will be 8 mod 9, which is 8. So if we had 8, and you can think about it, right? If we had 8 and we add 6, then we get 14. And 14, remainder 9 is 5. So do we have an 8 here? No, we don't. So then we basically can't do anything here. But we're going to store this in the hash map. So we're going to say, okay, we're going to store 6 at address 0. So our hash map will be 0 at index -1 and 6 at index 0. And the other thing here is if we get the same remainder at multiple locations, you want to think about, like, do I need to keep them all? Which one do I want to keep? So because you want to keep the smallest subarray possible, if you hit the same remainder multiple times, remember the thing we're deleting is from the last place we hit the remainder to where we are now. So we're just going to keep storing we're going to keep overriding the one we had because we want to have the biggest index possible because we're subtracting our current index from that index. So if remainder 0 occurs like here, here, and here, we're just going to always store the last one because the difference is going to be like where we are at now. So the tie is just always going to like go to the newest thing. And you want to think about those, like, do I want the longest subarray? Do I want it the shortest? Do I want all? And then for those, you would have different things. Okay. So we have a 0. So if we have a 0, what remainder are we looking for? So remember, I guess we can write this down. The current remainder minus the thing we're subtracting, which is this. Right? We want to get rid of something with remainder 7. So subtracting plus p, just to make sure it's a positive number. So plus 9 mod 9. So our current remainder is 0. We're subtracting 7 plus 9. So 0 minus 7 plus 9 is 2 mod 9. So we want something with a remainder 2. Because if we had something with a remainder 2 and we add 7, which is the thing we're trying to get rid of, then we'll have remainder 0. Do we have something with remainder 2? No, we don't. So we have this same value at index 1. So we're just going to overwrite it. Now we're going to be over here. We still don't have any matches for anything we care about. Okay, now over here, so we have a 5. So this will basically be 5 minus 7, which is -2 plus 9, which is 7. So we're looking for a 7. Do we have a 7? No, we don't. So because we don't have a 7, same thing. We're just going to store this thing at index 2. And keep going. And if you never get a match, then you basically just return -1. Okay, so now we have a 7. So if we have a 7, we have 7. We're subtracting 7 plus 9. So it's just 9 mod 9, which is 0. So we're looking for a 0. We do have a 0, which was at this index. So basically we're saying if this is a 0 and this is a 7, this thing between them had to have remainder 7, and then that's what we're deleting, right? Because our goal was to delete the smallest thing with the remainder 7. So that is what we have. And we have that by this hash map. So we're looking for a 0. We have a 7 at index 3, and 0 is at index 1. So it's just going to be 3 minus 1. It's just going to be everything after that last place. So this is length 2. And then we store this 7 at index 3. And so for this answer, it would be length 2. And you can't delete the whole array, so as long as your result is smaller than the whole array, then you return. So anytime you have a match, you can just minimize the result. So that's how example 2 would work. So let's go through the other ones because they're relatively short as well. Okay, so for this one, it's 3142. So let's just do that. And we can just calculate these remainders as we go, and then p is 6. So p is 6. And then what are we subtracting here? So our sum is 6, 10. So our remainder is going to be 4. So we want to get rid of something with the remainder 4. So we're subtracting 4. Okay. So same thing. At -1, we'll have, at -1, we'll put in a 0. So that'll be 0 at -1 for the empty array. Okay. So, so here, so we're subtracting 6 and 6. Okay. So here, our mod is 3. So we would do 3. We're subtracting 4. So -1 plus 6, which is 5. So 5 mod 6. We're looking for a 5. Do we have a 5? No, we don't. So we're going to store. Yeah, we're not even going to populate this. We can just do this on the fly. Okay. So we're going to store 3 at index 0 because that's the remainder. Okay, here we have a total of 4 now. So 4 mod 6 is 4. So 4 minus 4 is 0 plus 6 mod 6. So this is just 0 that we're looking for. Do we have a 0? Yes, we do. And so if we have a 0 at -1 and we have a 4 here, that means that this region, it has is remainder 4. So that's what we want. So this is going to be 2. And I think that is one of the things you can delete, right? If you delete 3, 1, this works too. So that is one of the solutions, but there's a better one, right? So, and then we're going to store 4 at index 1. And then here, so now we have 8 mod 6, which is 2. So we have 2 that we're subtracting 4. So -2 plus 6, which is 4. 4 mod 6, so we're looking for a 4. So we have a 4 at index 1. We have a 4 at index 2, which means, we don't have a 4 at index 2. We have a 4 at index 1. Which means we're subtracting this guy, which is just length 1. So that's going to be the best. So because we're subtracting this, it's going to be the best. And then we can keep going, but basically this will be the best because it's length 1. You can't do better than that unless it's empty, right? And if it was empty, then this whole thing would just be would just be 0 when you mod it by 6, which is not. And then the last one's kind of the same thing, so I'm not going to go into it. But basically, that's kind of the idea is, given a remainder, we know what remainder to look for. We can look for it in a hash map. If we find it, we just do that difference. All right, so let's code that. So, So I guess what we can do is we can use an array or we can use a hash map. I guess let's use a hash map. Sure. Or let's actually use an array. So we're going to use an array of remainders from 0 to p. And then we'll have an index, and then we'll just fill it or something. Yeah, actually, let's use a hash map. Let's use a hash map. So, okay, so integer, it's fine. Integer locations equals new hash map. Oops. Okay. Yeah, I think I used array in some other one. Okay. And then we're going to say, we don't even need to make this. First, let's actually get a total. So let's just get the total. And for num in nums, let's just add the total. And if total mod p equals 0, return 0 because we're done. Okay, so now the remainder we're looking for, we can call that like rem or something, equals total mod p. Okay. Okay, and then we can make our result equal to this. And then we'll just try to minimize it, and then we can go through all of our numbers now. So for We do need an index. Okay, so the value we're going to have, I guess actually we can do this here, so cur or something. So cur is going to equal cur plus nums I, and then we can mod it by p, because like I said, we only care about remainders. Okay, so we have cur, and now the number we're looking for, so we can call this target, and if we look at our picture, so it's going to be the remainder, which is what we have, which is the cur, minus subtracting plus p mod p. So this will be, yeah. So remainder, which is cur, minus the subtracting, which is rem, plus p, like this. So if locations contains the target, then we can minimize the result. Result and I minus. And either way, we're gonna store this this remainder at this location, and if there was one, we'll just override. Doesn't matter. So locations put cur I. Okay. And now like our result still might be this value, or it might be the whole array. So we can say return result is less than nums length. So if that's the case, then we'll return it. Otherwise, -1, because like we don't want to delete the whole array or anything. Okay, and hopefully it didn't screw anything up. I think this is int. Okay. Oh. Let's see. P3. Okay, I'm guessing. Oh, did I not? Okay, so if we're returning 0, so we screwed something up here for sure. If total mod p equals 0, yeah, this should be. If we're returning nothing, this should return here. So what do we screw up here? Total plus equal num. Is this like too big? Curious. Like maybe we have to make it a long. Let's find out. I don't think so. Yeah, I think the numbers are fine. Yeah, I don't think that's the case. So I'm doing something else. So let's go back, run it again. Maybe print the total or something. Definitely doing something silly here. Okay, so we are getting overflow. Yeah. Okay, so this definitely has to be a long then. I guess we can resolve that by modding by p at every step. Maybe that'll work as well. So hopefully that takes care of it, or we have to make it a long. Okay. Okay, well this is definitely not overflowing. So let's see what we did wrong. Okay, so we get the remainder, which is what we want. Yeah. And then, I guess, I mean, this will basically just be total. It should be the same thing. Yeah. Okay, so we get the locations. Oh, I forgot to store the empty array. Yeah, I forgot to store the empty array, I think is what it is. So let's try that. Okay. Okay, thanks. Yeah, so that's kind of the trickiest part to this, is figuring out, like, once I have a remainder, how do I know what remainder I'm looking for? I can't just delete something that, like here, like I can't just delete something that adds up to 6 or 5 or whatever. Like maybe you can in some of these, but you might also have to delete some other numbers, right? Like 5 or 11 or 17 or whatever. So that's kind of the tricky part to this. But overall, pretty good problem, to be honest. Teaches you some stuff about remainders, not super tricky, but pretty hard nevertheless. And I think this is, let's see. So we have the locations, which can all be unique. So I guess end. Yeah. Well, yeah, hopefully you learned something about like modular arithmetic and like how to get different things. Also, I guess I don't think I brought it up, but if you have, two remainders that are the same, think about what that means for like an array between them, right? Like if you have a remainder 5 here and a remainder 5 here, think about what that array between them has to total up to and things like that. So this is basically just a harder version of that kind of thing. But yeah, hopefully this is helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.